we have a few tricks for solving first-order differential equations exactly, but all of those tricks depend on the equation having a certain form or some integrals being doable. So what happens if the first-order equation that we have isn't in one of those nice forms, or involves some integrals that we can't do? Then what do we do? At that point, we kind of have to give up on finding an exact solution to the differential equation and instead find an approximate solution to the differential equation. So let's try to figure out how we could approximate solutions to a differential equation. So we are still talking about first-order differential equations. So we're going to assume our differential equation looks like this: dy dx equals some combination of x and y. And so how can we find an approximate solution? Well, one thing that we've looked at is we can, just with this differential equation, we can draw a slope field for it. And that's what I have here is just some slope field that is somehow supposed to represent every slope field, because, right, we don't actually have a formula here. But if we have a slope field, let's see, how could we sort of interpret the slope field to figure out what a solution should look like? Well, for one thing, we know that every differential equation that we've ever looked at has many solutions, infinitely many solutions, right? For a first-order equation, typically, if you have just one point, you can find a solution through that point. So I guess one thing that we're going to have to start with to narrow it down to just one solution is we're going to have an initial condition. And an initial condition for a first-order equation is just some point in the plane. So let's start, just to be concrete, let's start here. Okay, so we're going to have some sort of initial condition, y of x naught equals y naught, right? So this point that we've chosen here is the point x naught, comma, y naught. So our starting information here is x naught, comma, y naught. Okay, so now what does the slope field tell us about the solution that goes through this point? Well, remember, why a slope field gives you geometric information about a solution to a first-order equation is because every solution to the equation is tangent to any of these little line elements that it touches. So, right, we don't know what the solution is through this red point, but we do know that its tangent line at this red point has to be in the same direction as the little line element that the point is sitting on. So one thing we could do, I guess, is just follow this tangent line for a while. If we follow this tangent line for a while, we're going to end up at some other point down here. Now, one thing we're going to have to decide is how long is a while, and we'll talk about that in a second. But once we've followed this tangent line for a while, you see we end up on a new little tick mark. So we could call this new point, say, x1, comma, y1. And then since we're on a new little tick mark, we could follow this little tangent line for a while. That might put us over here, which would give us another new point, x2, comma, y2. And that puts us on a new little tick mark, and so follow that one for a while. And then just keep doing this as long as you, right, that gives us x3, comma, y3. And then just keep doing this as long as you feel like it's productive or as long as you need an approximate solution for, right? Remember, even on points where there isn't a little tick mark, the function f of xy will give us a slope that we could follow. So maybe it would be something like this. So you can generate as many points as you need to, and at every point, since you're just following a tangent line, it's going to approximate a solution. Okay, so that seems like a good idea, but we need to work out an actual formula that we could use here. And just to start things off, we need to decide how far are we going to move at each step. We're going to call that, how far we move for each step is a distance in the x direction. Right? The distance that you move vertically is really determined by the slope. So how far we move in each step is a distance in the x direction, and we'll call that delta x or h for short. Okay, so before we can start, we have to choose some value for h. On this particular one, it looks like h is about a half, but h. And h is the change in your x value. Okay, now as you go from one point to the next along this chain, you can see we're just moving over h each time. So to go from x sub 0 to x sub 1, we're just adding h. And to go from x sub 1 to x sub 2, we're just adding h again and adding h again. So what happens to x as you go from one point to the next isn't too mysterious. You just add h every time. So the tricky part is really what happens to y. So let's zoom in on one of these points here. So we have some point. This is, say, x sub n comma y sub n. So we're imagining that we've gone through this process of generating new points several times, and so we're at point number n. And there's some little line element here. And remember that the slope of this line is given by the differential equation. It's f of the x and y coordinate that you're at, and we're at x sub n comma y sub n. So that's the slope of that little line element. And we're going to follow this forward a horizontal distance h, which is delta x. Okay. But remember, slope, since we're following a line here, slope is just delta y over delta x. We have delta x in this picture, so let's add delta y to the picture. Delta y is right here. Okay, so we have delta y over delta x is f of x sub n comma y sub n. Okay, and we know delta x because delta x is always just h. So what we can do is multiply both sides here by delta x. And we get the change in y is f of x sub n comma y sub n times delta x. But delta x, remember, delta x is really just h. Okay. So we know delta x, it's h, and now we know delta y. So our new x coordinate, so we started with x sub n, so the next one is x sub n plus 1. So to get our new x coordinate, we take the old x coordinate and add delta x to it, which is h. Remember, h is just delta x. And to get our new y coordinate, we take our old y coordinate, which is y sub n, and we add delta y to it. But we have a formula for delta y now. Delta y is f of x sub n comma y sub n times h. Okay, so what this formula tells us is how to go from one point, one approximate point, to the next one. You just use the formula. Sub 1. Of course, once you've found x sub n plus 1 and y sub n plus 1, once you've taken one step forward, you can then turn around and take your new point, x sub n plus 1 comma y sub n plus 1, and generate another new point by using the formulas again. Right, so your old output point becomes your new input point. And then you can repeat this as many times as you want to generate more and more points that approximate a solution. When you join all these points together, like we have up here, they give you some idea of what a solution looks like in that region. Of course, it doesn't give you any idea of what a solution looks like in other parts of the xy plane. So you really have to choose an initial condition that you actually want to track, because this process only gives you information about the solution that goes through the initial condition you started with. So this process, this way of generating points on an approximate solution, is called Euler's method. It's not the only way for approximating solutions, and it's definitely not the best way, but it is the simplest way, since it has this nice geometric interpretation involving the slope field.